Hi, thanks for coming to my talk, which is about work that I've done with Carl Rothfels, trying to understand some rather mysterious behavior that we've observed when comparing birth-death models in a Bayesian context. An alternative title for this talk could have been something like, so what exactly are phylogenetic data anyway? And that sounds maybe philosophical, but actually has numerical consequences. And you can find a preprint for this work currently on bioRxiv. But this all goes back to an analysis where Carl and I, along with our colleagues, estimated a total evidence phylogeny for Moradian ferns, these tree ferns here depicted in the Pennsylvania. We noticed some fairly strange things when we compared birth-death models. So the data set for that analysis consisted of a bunch of fossils from the Pennsylvania. And these fossils are preserved in coal balls, which are found in Pennsylvania coal beds of North America in high abundance. And they preserve a bunch of species, including Moradian ferns. And the rest of the fossil record for this group is rather sparse. There are not very many species today. So almost half of our data set were samples from the Pennsylvania. So even before we did this analysis, when we sat down to plan out what models to use, we figured that fossilization rate variation was going to be a really big deal. And we are additionally interested in understanding how diversification rates varied. And we approached this using model comparison. So we were doing this in a Bayesian context. So we use Bayes factors, which are ratio of marginal likelihoods. If this number is larger than 1, it means support for model 2. If it's small, it means support for model 1, given a particular data set X. So the marginal likelihood of a model is the average probability of that data set under that model. So you calculate that for one model and you calculate for another model using an algorithm like the stepping stone sampler or some other special algorithm for calculating marginal likelihoods, plugging it into this equation and getting a Bayes factor. Sometimes throughout the talk, I'll report 2 log Bayes factors. So if that's larger than 0, that means support for model 2. If it's less than 0, that's support for model 1. Same number, different scale. So we did this. We began with a constant rate fossilized birth-death model. Purple is the fossilization rate. Blue is speciation, and red is extinction. We compared this model to one that allowed fossilization rate variation. Model fit decreased by 2.5, which was surprising. If we allowed diversification rates to vary, model fit increased by 25. That's great evidence that diversification rates vary. If we take that model and add fossilization rate variation, model fit decreases by 14. So regardless of the assumption we make about diversification rates, adding fossilization rate variation decreases model fit, which we found very surprising because we had that strong prior expectation that fossilization rate variation would be very important. So we've dug into this, and our explanation rests on an argument about what exactly phylogenetic data are. So we think of a phylogenetic process as beginning with a single lineage in the ancient past. That lineage has a character state or states that I'm representing by color. So we begin this process with the blue lineage in the ancient past. That lineage evolves and the group evolves by speciation, extinction, and character state changes. And occasionally there's a sample, either a fossil or an extant species that gets sampled. So there's some true history that we don't observe. Nonetheless, we want to make inferences about it, so we collect data. And as phylogeneticists, we think of the colors of the samples being data. So that's going to be something like a nucleotide alignment or morphological character data set or something. But the reality is that there's actually a taxon data set underneath those character data. And those taxon data carry information about diversification rates. And paleontologists use that kind of data in the form of fossil occurrence data to estimate diversification rates all the time. So we need to think about these things as data in and of themselves. As phylogeneticists, we often think about this sample tree, the tree that relates all of our samples, as being a parameter. And because it's a parameter, we want to put a prior distribution on it. And that prior will be something like a uniform prior, or coalescent prior, or a birth-death prior. And the birth-death process has parameters that describe sampling events, fossils or extant species. So really, we should be thinking about that distribution being a distribution on the tree and the samples. The samples are observations. So the probability of those samples should be a likelihood function. So returning to model comparison, stepping stone samplers and related algorithms that compute marginal likelihoods require that we identify particular terms in our equation as likelihood functions. If we do that incorrectly, we will get the wrong marginal likelihoods, which will compromise our ability to compare models. An alternative for comparing models for computing base factors is to place a prior on the models and then compute the posterior distribution of models. And we can do this, for example, using reversible jump MCMC, where we use MCMC to generate a sample of the models, which are proportional to their posterior probability. So we can plug in all the necessary terms into this equation and compute a base factor. These are two theoretically equivalent ways of computing the same number, base factor. And if you're not convinced, I can prove it by simulation. So I simulated a bunch of molecular sequence data sets with this many species. I computed base factors using marginal likelihoods on the X and reversible jump on the Y. And indeed, there's one-to-one agreement because these are just two ways of computing the same number. If I do the same thing with the same sequence data set, but compare a Yule model to a birth-death model, things go wrong, which is quite disturbing. But the base factors seem to be off by a number that's a function of the number of species, which is gives us hope that maybe we can understand what's going on. Another thing to mention is that these gray areas correspond to when the two approaches disagree about what the preferred model is. So it's not just that whatever error is happening is decreasing model fit or decreasing support. It's actually driving support to different models. So it can be misleading. And if we do this with a fossilized birth-death model, like a constant fossilized birth-death model versus a variable rate one, we see the same patterns. So these theoretically equivalent approaches give us different answers, which is fairly disturbing. What that probably indicates is that they're perceive the data to be different. And to explore that idea, I'm going to talk about this principle of sequential Bayesian analysis, which is exemplified by Lindsley's famous algorithm that today's posterior is tomorrow's prior. So you collect an initial data set, specify a prior distribution, you update that prior distribution into a posterior distribution based on your data set. Collect a new data set, and you use the previous posterior distribution as your new prior, you get a new posterior. You're continuously updating your posterior distribution as you collect new data. And in this context, that would look something like this. So we would collect taxon samples, and we would want to estimate the posterior distribution of diversification parameters as parameters of the birth-death model. So that would be a function of the likelihood function, the probability of the taxon samples given the birth-death model, the parameters of the birth-death model. We would have prior distributions on those parameters, and we would calculate the marginal likelihood of the samples under the model. That would be the first step. In the second step, we would collect new character data. So we took our samples and we threw them in a sequencer, or we recorded their morphological states. And now we're interested in inferring the tree that relates to those samples. And we also have a substitution model which describes how the characters evolve. The posterior distribution for the second step would look like this. We would take the prior from the first step and plug it in as our new prior on diversification rates. We would then calculate the prior probability of the tree, conditional on the samples and the updated diversification rate parameters. Then we would calculate the probability of the character data given that tree and substitution model. And that would be a likelihood because it's a probability of some observations. Importantly, the marginal likelihood in this step is just the marginal likelihood of the colors, not the marginal likelihood of samples, because we already computed that in the previous step. A more normal thing to do, what we do when we sit down at a computer and actually use this method, is to do a joint analysis. So we analyze both of the data sets at once. And in this context, conventionally, we would label this distribution on the tree a tree prior. This would be a prior probability, but as we've argued, we think that's a mix of a prior and likelihood function. But if we did this correctly, the marginal likelihood of the joint analysis would be for both the colors and the samples. A critical piece here is that whether we do a sequential analysis or joint analysis, at the end of the day, our posterior distribution of the tree and other model parameters is identical. It doesn't care whether you analyze them simultaneously or one at a time, it's the same. So how does this help? Well, it allows us to make some theoretical predictions about the errors that we observe. So the marginal likelihood of the joint analysis is the product of the marginal likelihoods of the two steps. I can label all those terms by a particular model. So I calculated these things for a given diversification model, right? And in this case, that's M2. And then I can divide by the same terms from another model, M1. And the result is a bunch of base factors. One is a base factor for the joint analysis, which is the product of the base factors for the two steps. So if I sit down and I do a joint analysis, But in reality, for some reason, I end up doing sequential analysis. My marginal likelihoods are going to be off by this ratio, the ratio of the marginal likelihoods of the samples. So if I return to the Yule and birth-death simulations, what I see is that if I compute that ratio, it perfectly explains what we observe about the discrepancy between these two approaches. So what that means is that our conventional phylogenetic representation, where we label the probability of the character data as the likelihood and the only likelihood, is actually equivalent to doing a sequential analysis. The second step of sequential analysis. So that's what theory and simulation says, but what about like real data? So we return to the Muradi's data set, we fit a constant model and a variable model. If we use marginal likelihoods, we favor the constant model by 3 2-log base factors. But the variable rate model is preferred by 18 when we use reversible jump. Very strong support for variable diversification, variable fossilization. And the result is a very different estimate of divergence times, up to 15 million years. So it's really important that we're able to accurately compare birth-death models. So what do we do? Well, one option is just to use reversible jump, and CMC I've proved that works, right? That's kind of selling reversible jump short, because really it's a model aggregate tool, not a model comparison tool. It alleviates the need to choose one particular model because it just averages over all of them. But nonetheless, if you were interested in testing different diversification models, you could still do that. The tricky thing is that it's difficult to design reversible jump proposals, and usually it restricts you to a certain set of models that maybe they're nested or constrained in some other way so that the Markov chain can work efficiently. So it's going to limit what you can do, but so by contrast, marginal likelihoods, you can compare arbitrary models. So it'd be really great to have generic, correct marginal likelihood estimators for these types of models. And to do that, we would have to develop theory that partitions the prior and likely components of tree models. So if we think about this tree prior as a mix of some likelihood and a prior function, prior probability, we can use probability theory to manipulate this equation in such a way that the likelihood, the probability of the samples is unambiguous. And in fact, we can do that with the Yule model and birth-death models. And indeed, it restores base factors, which is great. However, it's going to be very difficult to do that with fossilized birth-death models or any model that has non-contemporaneous samples. There's a bright side, which is that this allows us to think about using posterior predictive simulation, which is a tool for assessing model adequacy. You simulate data under a particular model. You compare that data to observed data. If it matches, that's good. It means your model is doing a good job. If it doesn't match, that means that your model is failing to capture the true process in some important way. So if we think of taxon samples as data, that's a strong justification for using posterior predictive simulation to assess birth-death models, which we're really excited about. So with that, I'd like to thank my collaborators on the Muradi's project, as well as my colleagues and friends who've provided a lot of feedback, and in particular the Rothfels Lab, Sensu Lato, my institutions, my funding resources, computational resources, and the Reverend Bays. With that, I'll take questions. Thank you.